Okay, I'm gonna do this over.
Okay, I'll wait.
Okay, thank you. Okay, I'm going to the module page for Engineering 35, on Engineering 35 Canvas page. I want to remind you that you guys have an expert tech support team to help you with all your Canvas problems. Don't come to me because I'm not an expert. I'm going to give you some suggestions that may not even work. So the Computer Technology Center is there to answer all your questions. It's exactly what their job is right now this semester. Support students in Canvas. So when you have a question, ask them, okay? And if you learn something like, oh, Joanne, because you did this, that's why I can't get on Canvas, then you send me an email, or I guess actually contact me through Canvas to let me know what it is that, what I need to do, okay? That's our rule now. You contact them, tell me if I need to do something. David, I'd like to keep going because okay, why don't you ask your question quick?
No, don't worry about it. It's a Canvas question, so I can
Okay,
I can
good.
ask
I'm
them.
not going to answer it. Okay.
Right.
Next thing is the summer work. Some of you had problems accessing. Make sure you watch the video first before you do the homework. Otherwise, I'm probably going to make you redo the homework because it's not following the format. Like I said in class on Tuesday, this class is not just to teach you statics, but it's to teach you presentation in engineering, how to present your work as an engineer so your bosses and peers can read it and it's clear. So presentation is very important. So if you didn't do it, watch the 2D component video first, then do the homework 1, then watch the 3D component video, and then do homework 2 and submit it. And the solutions are here for you to check, okay? And the solutions there are so that you could check your numerical values. Next, syllabus. I do not think I went over the syllabus. Did I? Let's look at it. I don't think
you did go. I think you did go over the syllabus last time.
I did? Excellent. Yeah. Great. I don't have to go over it. Sometimes I go over it in my head so many times and then I'm not sure if I actually mentioned it to you guys or not.
I remember we went all the way up to the part, I think we covered the book part, so I remember that we actually went through it. I think we got through the whole thing.
Okay, and I remember now that I did tell you there's no large exam, it's quizzes and the percentages. Thanks, Adam. Okay, next thing is I want to remind you that if you want a quick visual on what's due when, is go to the calendar. So I'm clicking on the calendar right now, and you go up here to go see it says September. You could have looked back to see what was due in August. Here's September. There's nothing written down in October. I'm just a few weeks ahead of you. But here is a quick way of seeing what is due. I know also in the student view, you have a way of looking at what's due on the right side, but for me, I think this calendar is better. I'm definitely more of a visual person in terms of, like, I have a pretty good, really good memory of memorizing students' names, but it's all spatial. Like I can know where you sat, or if I remember a conversation I had with a friend, I can remember which side of them I sat on. It's just, that's who I am. But you could determine your own way, but for me, this is really clear. Okay, now I'm going back to the Canvas page for 35. And one thing that we did not, I'm going to modules. One thing that we didn't do on Tuesday that I was hoping we would get to is do an icebreaker where we break up into groups and you guys start to get to know each other. And we're gonna do that at the end of today's class. And I also want to, I'm gonna stop sharing for a moment, and I wanna introduce you to Andrew. Actually, let me just give you a little background on myself, and then I'm gonna have Andrew give you his background as well. So many of you have heard this spiel already because you've had me in previous classes, but I grew up in New York City, not in Manhattan, but in Flushing, Queens, kind of a blue collar area. My mom was a stay-at-home mom. My dad worked for the equivalent of PG&E as a gas guy. If you had a gas leak in your house, you would call Con Edison is the company there. And he would be one of the guys driving around in a van to help. Neither of my parents have an education. My dad never finished grammar school. My mom went to a 2-year secretarial high school, so she never really finished a 4-year high school either. But I really did love school. I liked school. I really loved math. And I just persisted in school, and I did well, and my parents encouraged me. And I did go to Catholic school because where we grew up, the public schools are really, really bad. So I was raised Catholic, but I'm not Catholic anymore. But I think that, I was raised Catholic, and I did bring the Girls in Engineering Middle School program that we run in the summer to my high school. I went to an all-girls Catholic high school, and I really loved that. So we brought the Girls in Engineering Middle School program that we run here at Cabrillo to my high school. So I am in touch with my physics teacher and my trig teacher and my English teacher. They're still around. They're really awesome women who are nuns who gave up their life to educate girls. And I want to even tell you this. I think this is a really interesting tidbit, and I guess it has nothing to do with statics, but I went to high school in the 80s. I went to the all-girl Catholic school on the East Coast, which is very conservative. And during health class, they passed around all the different contraceptives. Isn't that totally progressive and totally right on? They really were it was so important to them that girls don't get pregnant and they finish their education so they could support themselves, that they did that in the 80s. I mean, that is just unbelievable. So I think it's a pretty fantastic school. I wanted to be a math teacher, but a lot of the girls in my classes all were going to be teachers or nurses, and I wanted to do something different. And I really, like I said, love math and science. And I used to do a lot of crafts at home with my family. So I thought about architecture, and I took a class like our Engineering 5 class for architecture, and I really didn't really like it. And somebody said, why don't you go into civil engineering? It's similar to architecture in that you're designing things, but it's more based on math and science and practical application. And so that's what I decided to do. I went in for civil engineering, and the favorite specialty in civil engineering that I loved, Mackenzie, was geotechnical engineering. And so I was told in order to be a geotechnical engineer, I have to go to grad school. So I went to graduate school. I lived at home, and I went to a 4-year university that offered me a full scholarship. Otherwise, I wouldn't have been able to go straight to a 4-year school. Then I went to graduate school at University of Maryland, which is just outside of DC. So again, I grew up near a big city, but I was in driving distance of coming home. And it was good because my dad passed away then. So I was able to come back and see my mom, my sister. While I was in grad school, I was given the opportunity to teach, and I started teaching engineering, and I loved it. In fact, when the materials teacher went on sabbatical, I taught the whole materials class as a grad student, and I knew then that what I wanted to do was teach engineering. I had always thought about living in California. If you live in New York, what's the next best thing to experience is California. So I lived out in California for the summer, and I worked for a geotechnical engineering firm, and I just loved it. I was in the Bay Area. And so I knew when I graduated, I wanted to live in California. And when I moved out here, I worked for a construction company that did specialty geotechnical work. It's called Hayward Baker. Mackenzie, in case you want to hear about it, Hayward Baker. They were centered in Ventura, and I wanted to work in engineering first because I wanted to get engineering experience before I taught engineering. And I traveled around a lot because it was a construction company, and that was really awesome. And then I started learning about the community college system, where the focus is teaching and not research. And eventually I moved up here because I met a guy who I wound up marrying. And I now live in Santa Cruz since 1990. I got the full-time job at Cabrillo in 95, and it was awesome. And I really love my job. So I'm here, like I said, not just to teach you statics, but to be your support, to get through the program, find a path for yourself and all that. So I love what I do. Andrew. So Andrew is our TA for the class. He took Russell and Rob's class last year. So he but he is reviewing all my notes so he could see how Carl, Karen, and I would present statics, because Russell did it in a little different way, but Rob does the same thing that we do. So Rob, Karen, Carl, and I teach statics the same, but I think Russell taught it a little bit differently. So Andrew, would you give them a little bit background of yourself from high school on?
Yeah, totally. So I'm from here. I went to Soquel High, and I ended up doing my freshman sophomore year at Soquel, and then I did independent studies and graduated a year early. I then went to Cuesta Community College for a year, and at this point, I really didn't know what I wanted to do. So I I have like 180 college credits right now, so I could have already got a bachelor's if I would have known what I wanted to do. But I really wanted to travel and kind of figure it out. So I did that for a year. Then I moved to Oahu, Hawaii for a year, and went to school out there. Then I moved to Santa Barbara, and I stayed at Santa Barbara for 2.5 years. And that's really where I figured out that I wanted to focus, to stay on engineering. When I was in high school, it was always engineering, and then somehow that kind of got lost in the shuffle, and I needed to try other stuff before I figured out that this is what I really wanted to do. And then I went to Cabrillo, and at this point, I was like, okay, all I need to do is get a degree in engineering. So I want to do the path of least resistance. And so I looked and I said, oh, civil engineering, least amount of classes, I'm going to do that one. But then I talked to Joanne and Carl, and I really started to figure out what type of engineering resonated with me, what kind of jobs I wanted to get. And so I resettled on mechanical engineering. And yeah, I'm really happy about that. I plan to transfer to San Jose State for fall of next year. So these are my last 2 semesters here at Cabrillo. I've already finished all the physics, all the math. I took statics and dynamics, and so I just have a few other engineering classes that I need to wrap up. And yeah, so that's where I'm at now. Hopefully I'll be able to finish strong here at Cabrillo and then get a good internship this summer. So that's like my next big goal. And yeah, that's pretty much it.
Hey, Andrew, you said you were in Santa Barbara for 2.5 years. Were you going to school or working, or what were you doing there?
Yeah, so I was going to Santa Barbara City College, and so because I graduated early and everything, by the time I stopped my sophomore year at school at Soquel, I already finished all the math I needed to graduate. So when I did independent studies, I didn't do any extra math. So when I got to college and I decided, oh, I want to do engineering, pretty much had to start my math from pre-calculus level. So so when I got to Santa Barbara City, that's really when I started on that course and did the first 2 calculuses and pre-calc and trig. And so yeah, so that was pretty much my whole Santa Barbara City college career. And yeah, at Santa Barbara City, I was a tutor for the astronomy class, and I was a tutor for math.
Okay.
Along with that, yeah, I worked at the Santa Barbara Yacht Club. That was right across the street from campus. It was pretty cool.
Okay.
Yeah.
Thanks, Andrew.
Uh-huh.
So you guys will get an opportunity to work with Andrew. When we have breakout rooms at the end of class today, he and I will keep going into different rooms. You'll get to talk to him. And then he'll also be participating in the labs too. So he and Rob are working together. So you'll see him in the lab too. Jack, I noticed you're having your name John. Would you mind changing it? Go up to the right, the 3 dots, right click on it, or no, just left click on the 3 dots and change it to Jack. So just so that everybody knows you want to be called Jack. Okay. And I think everybody else has the name they want to be called. Great. Thanks. Okay. So my notes here, syllabus, calendar. Okay. So we're going to start the lesson now on resultants. So what's our goal today is we're going to talk about resultants. we're going to work through a 3D problem, which is also going to give you more exposure to the process for doing components in 3D. And I picked a 3D problem that has both the distances given in the angles. And I think that's like something that's really new to you, looking at a 3D problem. So you'll get, besides listening to the video of the 3D components and then doing homework number 2, you're going to see it again because I'm going to start the process exactly the same way. And that's how we're going to approach all the statics problems. And then after that, we're going to go into breakout rooms, and you're going to talk to each other and answer a few questions to get to know each other. And then you're going to start working on the dot product workshop. And some of you I saw submitted already, so some of you already are experts. And I think what I'll do is when you go into the breakout rooms, I'll post the solutions so you can look back to that too. So when you're in that breakout room, you're going to get to know each other. You're going to work on the dot product workshop, and then you could start doing your resultant homework. Okay. And the resultant homework is 2 of them. There's homework 3 and homework 4. 3 and 4. 3, I think, each one of them only has 2 to 3 problems. So again, I'm giving you more homeworks, but less homework problems in each homework. Okay. But again, you have to be proficient in statics. So after 2 problems, if you feel like, you got to be your own judge. If you really don't feel like you got it, you got to do another problem. Okay. And you keep doing another problem until you really got it. Okay, so I am going to turn on this overhead thing. I met up with a couple of students yesterday, and in my office hours, remember my office hours are 1 to 2 every day. Tomorrow, not though, sorry, I have an appointment. It's the first week of school. So tomorrow, no office hours, but every other day, 1 to 2. And of course, Monday, you know, is a holiday, which I'm glad we don't miss a class. But anyway, yesterday people said, well, why don't you use a whiteboard? A whiteboard is a little uncomfortable for me because first of all, I don't have a place to put it. I'm like cramped in this little corner in my living room. I don't really have a place. I'd have to stand up, meaning I have to figure out how to do the video and the standing up and not move too much. And I tend to jump around a lot in class. And then also I don't really like the smell of it, and I don't want it in my house. I don't mind it in the classroom. So, but what I am going to learn, so you have to give me maybe a week or so, I am going to learn how to just write straight on my tablet, because this summer I did buy a Surface, so I could do that, and then it probably would be a bigger screen. But until I do that, bear with me on writing. Okay, so I'm turning this on, so good. Okay, so now I am going to close the chat screen so that I could see you guys more. But Andrew, I'd like you to keep an eye on the chat screen for me and interrupt me if somebody's asked a question. And otherwise, those of you that I could see, you could raise your hand and I could see you. You could do the virtual hand, or you could just put your hand up. Again, I mean, I would love it if everybody could turn their screen on, because as a teacher, when I see your faces, I could see what questions you have. I could read your face. But if you're not comfortable, I mean, you could put a background behind you. You could choose it in Zoom so that you don't have to show us the room you're in. If you don't have a webcam, that's what they're called, right? A camera. If you don't have a camera, you could borrow them from Cabrillo. So put your name on that tech list. I've already posted about that. Okay, so this is the problem we're working on, and let me just move my screen so it's vertical for you. This problem is also on the module for today. So I don't know how well you could see it, but we have 2 different forces here. And what I want to start out with first is to say, really in this lesson, we're really doing we're looking at dynamics, because our resultant is not equal to 0. When we do statics, we're going to say the resultant is equal to 0. But every author of every textbook and every teacher of statics first wants to make sure that everybody could calculate resultants. So we're really not doing statics now, right? Because if we were doing statics, what would the resultant be? Adam, what would the resultant be if we were doing statics?
It would be 0.
Zero. And you guys may have seen my announcement. When I teach in a classroom, I just go around the room and ask questions. And if you're uncomfortable, then you could just say pass. Well, going around the room really doesn't work here because your pictures sometimes move to a different place. So I alphabetized you by first name and I sent you that on announcement. So I'm just going to call on you. And if you want to, you could just say pass. And Andrew, keep looking at the chats, okay?
Okay.
Okay, so first few is Adam, Amani, Angel, Bon, Colin, Daniel C, Daniel H, Daniel I, David L, and then David LR, and then Edgar and Elizabeth, okay? So probably what you want to do is figure out who you're after, and then you know, and then I don't have to call your names. Okay, so we are really doing a dynamics problem because the resultant is not equal to 0. And what I want to point out, which maybe some of you have watched the force video already, it's next week's class, so you may not have, but notice this point right here. Both of these forces are coming off the point. When forces come off a certain point, the only type of rotation you could have is linear motion. And linear is a fancy way of saying linear motion is translational. So you could imagine that if this body here is being pulled this direction, it's somewhere the resultant is going to be somewhere around here. It's just going to be pulled. It's not going to be spun. It's only if I have a body. So this is called, when I do this kind of thing, these forces are called concurrent forces. And the definition of concurrent forces are forces acting at the same point. Concurrent forces are forces acting at the same point.
And at the same time, or no?
Yeah, we're always looking at it at the one time, instantaneous. So when we do statics for this, it's called statics of particles. Because the body is reduced to a point. It's called statics of particles. And when you look at the topics we cover in statics, one of the topics is statics of particles. If we had a body, though, that had a force coming through the center, a force going here, a force going here, and a force going here, this is not, could you imagine that if you had a body that was being pulled not only at the center, but also in other parts, you're going to have linear motion, but you're also going to have rotational motion, or the potential of linear and rotational. Certainly, if all the forces add up to 0, there's no linear motion. But if the rotation, if the moments add up to a value, there's going to be rotation too. This is called, did I spell it wrong? Rigid, yeah. Rigid body statics. You see the difference? The difference is that here we are drawing a free body diagram of just a point. So it's called statics of particles. Here we're drawing a free body diagram of a whole body that has forces in other places, not just in the center. So it's called rigid body statics. So Amani, what are these two forces called? What are they called? What's the word here?
Concurrent forces?
Concurrent forces. And because all the forces are coming off the same point, what's the only kind of motion you could have, Angel? If all the forces are coming off the same point, what's the only kind of motion you could possibly have?
Translational or linear.
Right, same thing. You could just say one of them. You could say translational if you want to be fancy. You could say linear if you don't. Okay, what about, so Bon, if I have a rigid body that has forces all over, what's the potential of motion that could happen?
Well, you're gonna have linear, but you can also have rotational.
That's right. You could have both. Okay. And in this case, so Colin, in this case where we have the whole body reduced to a point because all the forces are coming off the point, we're looking at statics of what?
Particles.
That's right, particles. And in the situation, Daniel C, where we have a rigid body where forces are coming off different points and could cause rotation, that's called what kind of statics? So Daniel C,
Body statics.
say it again. Oh, Colin, did you just answer the question again? That's fine. So what did you say?
Rigid body statics.
Rigid body statics. So when you watch the video on forces and motion, you're gonna hear this spiel again. So now what I'm doing is I'm going back to this problem. So what are we looking at? We have an F1 and F2, and I tend to always label the forces with a variable. And the reason why is so that I could refer it to as F1 and F2 than saying the 200-pound force, the 300-pound force. So typically when a problem is given in statics, I always put a variable on it. So then whenever I write about it, I could just write F1, okay? Now, whenever you do a 3D problem, and I said this in the video, first thing you do is look at where the axes are, because you don't want to mess that up. The X and Y axis is the vertical, creates a vertical plane, and the Z axis is coming out towards us, okay? We have two forces, F1. F1 is given distances. So when we find components, are we going to use angles or ratios? Daniel H. Is Daniel H here? So Andrew, you're going to have to help me on that too. I don't know who's here or who's not. I can't see everybody. I see Daniel C. I don't see Daniel H.
He's not here yet, no.
Okay. And Daniel Shaw, you're Isaac, right?
Yeah, you put me after Hyoji, that's fine.
Right. So could you change your name so it doesn't say Daniel up
Oh
there?
yeah, it unchanged itself, my bad.
Yeah, so people know who you are. Thank you. Okay, so we're going to find it using ratios, and then Daniel I for F2, we're going to use angles, right? Okay, so I'm just going to start going through this, and I'm going to start saying, and I'm going to set this up the way we did in homework 1 and 2. Can everybody see what I'm writing? F1 is equal to, I'm putting the force first. Then I'm taking a look at this and I'm noticing, this is another video you're going to be watching because you have to get better at 3D spatial visualization. So I'm not going to do it with coordinates, which is one way I show you in the video. I'm going to do it by just visually looking at it. When I go from this point, and let's call this point A, and let's call this point B. When I go from point A to point B, and this is my X direction, how much am I going over in the X? So David L, going from A to B, how much am I going over in the X?
Let's see. I think I'm Dave L. Wait.
Yeah, David L. David Lopez, I'm going to give you David L R because there's two David L's.
Okay, my bad.
Okay.
Hey,
All right.
Joanne, can you make it a little bit more clear? It's a little blurry for some
Yes.
people.
And what is blurry? Is it the picture that's blurry or my handwriting?
It looks pixelated a little bit, so.
Okay, let's focus. And thanks for you guys tell me this, all right? Is that any better?
I don't think you're going to be able to fix that.
Really? Okay.
It's not the focus. The focus is fine.
It might be because I zoomed in too much.
But I'd prefer.
Let me
No,
zoom in
that's
a
not
little.
better. That is not better.
Not
Did
better?
Did you
I mean,
print
it's
this
better in
out,
the
Joanne?
visualization, but it's harder to parse the whole image. It's just it's confining.
Okay, what might be the case is because I have this picture that I printed and I have it in front of my paper and it might be focusing on two different things.
Again, it's not the focus, it's the resolution, which might either be your document camera or a limitation of the platform.
Okay, can you read it? Because obviously I don't want to spend 20
I
minutes.
can read it. Yes.
Okay. All right, so I'm going to look at only this for now. So going from point A to B, and I'm looking in the X direction, look for the distances that are parallel to the X. David L., how much am I going over?
Okay. In the X direction, it goes +2.
Great. Okay, how about in the Y direction? Take a look at the Y axis. What distance is parallel to the y going from A to B? David L.R.
The 5 inches.
Correct. And then Edgar, going from A to B in the z, what is the line? Look at the distance that's parallel to the z direction.
3 inches.
3. And is it positive or negative?
It's negative.
Negative. So going from A to B, it's going back, it's going negative. So I am going to write positive 2i plus, help me, x, y, 5j minus 3k. And I'm going to put the units, and under it, I'm going to put whatever that hypotenuse is. So we're looking at 2 squared plus 5 squared plus 3 squared under the radical. So this is my distance, and my distance turns out to be, I have my solutions here handy so that we don't have to punch numbers. Where did I put it? I have 38, radical 38. So now I'm going back here, 38. So again, just like in the component homework, we first put F1 is equal to, you put the magnitude of the force, you put the unit vector piece here. In this case, it's based on distances, and then you put your units at the end. And in the end, it comes out to be 200 times 0.3244i plus 0.811j minus 0.4867k, and I put my units. Be sure, whenever you put an equal sign, always make sure you have your units. I know in physics, they just tell you to put the units at the end. Whenever you have a variable with an equal sign, put units. I also want to mention, am I going too fast? No. I also want to mention, notice that I spend the extra time to put the 0 dot. And I want to tell you why. When you're writing things fast and you put a decimal, like let me just do it up here for scrap. If I write .3244 and you do it by pencil, there are times your dot doesn't show up, right? Right? When you put a dot sometimes for a period or a decimal, it doesn't show up. And if you don't put the 0 in front, it could, somebody, or the reader might think it's 3,244. So I always put this, because if my dot doesn't show up, they know that there must be a decimal there because you never put a 0 in front of a whole number. So that's my suggestion, but you do what you want to do. Okay, and F1 turns out to be 64.9i plus 162.2j minus 97.3k pounds. Okay, and I'm going to block it in, and this is in vector form. I want to make sure that I do my checks. So I'm going to do the 0.3244 plus squared 0.8111 squared plus 0.4867 squared equals 1, and I already checked it, so I know it works. I did 64.9 squared plus 162.2 squared plus 97.3 squared, all under the radical, and I already checked it, and it comes out to be 200. Let me just tell you that I am going to post the solutions to this problem. So if you find that you learn better by just paying attention, you don't have to write it, because it will be, I will post it. And then the last check is Elizabeth. Is Elizabeth on? What's the last check? I have a unit vector check, I have my magnitude check, and what's the other check I have to do? I don't know if Elizabeth's on. Okay, Eric, Brighton?
Visual check?
Right, the positive, negative visual check. And let's take a look. Look back at the picture. Going from A to B, it's definitely a positive X, it's definitely a positive Y, and it's definitely a negative Z. And sure enough, this shows up, and it's okay. And just as a side, let me just put it over here. In engineering, when it doesn't work out, you do this. No damn good.
That one we can't see.
Oh, okay, great. And that's the funny one. That's the most important one to see.
I'm sorry I killed your
No,
punchline.
it's okay. I'm glad you, no damn good. But you're never going to write no damn good, because when it's no damn good, you're going to go back and do the math again and fix it and then do this in the end. Okay? All right. Now I'm going to do the same thing for F2. So F2 is equal to 300 times. Now we're looking at an angle problem. I want to stop sharing for a minute. No, I'm not sharing. I just don't have me on the screen. I want to be on the screen. So again, this is in one of those little video lessons too, but just so that I want to just tell you again, and you also saw it in one of the other videos. So first, it's a 3D problem. I'm showing you a 3D axis. First thing you do, look at where the axes are. I'm up to Gerardo. What axis does this say? Are you there?
He's here, but his mic's off.
Okay.
Yeah, sorry, hi.
Okay, what axis is this?
X,
Good. What axis is this?
that's Y.
Great. And what axis is this one up
Z.
top? Z. So notice this axis is different than my picture, right? Okay, so you always have to look at the axes. Here's my force. The point is whenever you want to find a component of a force in the direction of any direction, you take the magnitude of the force and you multiply it by the cosine of angle to get to that spot. So you could imagine if you're riding a bicycle and you're sitting upright on a bicycle and you know what your weight is, you could find the component of your weight in any one of the bars in the bicycle, as long as you could measure the angle from my body, my weight, to that bar. So it's the magnitude of the force times the cosine of the angle to it. So if I had some funky axis out here, do you see my pen? If I have a funky axis out here and here's my force, that's all I do is I take the magnitude of this force and multiply it by the cosine of this angle to bring it to that axis. So that means we could move this force anywhere we want to find out what its component is. Okay? So now I'm going back to the overhead. Yeah, so the fact that there's a problem with the focusing, I'll definitely get on that using the tablet, but I have to learn it first. Okay, you could see this. So if I am looking at, again, I want to remind myself where the axes are. Here's X, here's Y, and here's Z. I'm looking at this force. How do I get it to X? Well, it would be really nice if I had what theta X is, which is theta X is the angle between the force in question and the positive x-axis. And to find theta y, to find the y component, it would be awesome if I knew what theta y is. And it would be awesome, is it awesome? Do we know what theta y is? So where are we? We are on Hyoji. Do we know what theta y is? Now, I have to tell you, Hyoji just joined the class a couple of days ago, so she might, have you done the 3D component homework yet?
Not yet.
Okay, then let's skip you. Just say pass. Isaac, do I know what theta y is?
Yeah, theta y would be 60 degrees.
Right. And how did you know?
Because we don't have to do any tricky math. We already have 30 degrees off the
Right.
or off the XZ plane.
That's right. They gave us the 30 degrees between the force and the projection to the XZ plane. So this angle, you know, is 60. Okay. How about now theta Z? Jack, did they give us, and oh, Jack's in the same boat about the components. Jack, do they give us what theta Z is?
Yeah, it's 40 degrees.
Okay, so no, it's not. So you still have to watch that video.
Oh, wait, no.
Yeah,
It's,
right, because
yeah.
take a look at this. What the 40 degrees here is the angle between the projection of that force.
Yeah. So
right, on the plane. So this 40 degrees is not theta z. They did not give us theta z.
it's not the most
The
direct.
theta angle is always the quickest way to get to the shortest angle to get to the axes. So in this case, theta y is awesome, it's given, but the others are not. So let's do this now. We're looking at the x. So they didn't give us theta x. So I have to take the force. I'm going to swing it down, cosine 30, and then swing it over. 40 plus 90 is 130, right? I. Plus theta y they gave us, cosine of 60. And I should put the degree symbol. And then j, plus theta z would be cosine. I swing it down 30, and then I swing it over 40. Okay, and we're looking at pounds. Okay, so this comes out to be, my second step is I set it up with the unit vector. It turns out to be negative 0.5567i plus 0.5. Remember, unit vectors are supposed to be 4 decimal places. And then this comes out to be negative 167.0i plus 150j plus 199.0 k pounds. And I'm going to box the answer in F1. And then I'm going to do my checks. I'm going to do my magnitude check, 167 squared plus 150 squared plus 199 squared. And I already checked it. It came out to 300, so it's okay. Am I getting off the screen? No. And then I'm doing the positive negative visual check. Let's take a look back at the picture. Z should be positive. Y should be positive, but X should be negative. Good. And then I'm going to do the unit vector check. 5567 squared plus 0.5 squared plus 6634 squared equals 1, and it does. Okay, so I'm giving you now, you watched me do it on the video, standing up. Now you watch me doing it sitting down in the paper. And the fact that this problem has both a 3D angle and a 3D ratio problem is good practice. So now I'm going to pull this page off. And I'll put it above. Okay, I'm just following my notes to make sure I have everything. Okay, so now what I'm going to just talk to my I don't need to be, you don't need to be looking at me. Okay, you guys already know what resultants are, right? Resultant is a vector sum of something. In physics, you learn 2 different ways to do it. One is graphically using the parallelogram rule, right? Do you remember that? Shake your heads. Do you remember the parallelogram rule? You know, a little tedious, but fun. Okay. The other way of finding vectors is by just adding the x component, the y component, and the z component, right? Maybe a little bit easier, maybe not as fun. We are not going to do the parallelogram rule. You already know how to do it. You could do it, but we're doing the vector way in this particular problem, just so that we don't take up so much time doing all the drawings and stuff. Let's move along. Okay, so I'm doing it by vector sum. So my resultant vector is going to be equal to, so can you, I don't know if you could see, I'm going to just keep flipping back and forth. F1x is 64.9 and F2x is minus 167. So that means this is I plus J 162.2 plus 150.0, and this is J plus negative 97.3 plus 199.0 K, and it's all pounds. So the resultant force comes out to be negative 102.1 I plus 312.2 J plus 101.7 K, and it's pounds, and I'm gonna box it in. Okay, so I'm not sure what you guys do in physics, but in statics, when you get a resultant force in vector form, you also want to express it as a magnitude. Did you have to do that in physics? Okay, so I'm going to find out that the resultant is 102.1 squared plus 312.2 squared plus 101.7 squared, all under the radical, and it turns out to be 343.9 pounds. And I do like to box things in, and I don't want to box in my whole calculation. So what I'm going to do is just do this, equals R. Okay, how's my speed? Let's see, thumbs up. Do I need to go slower? How am I doing?
Good.
Okay.
Good.
Okay. So now, in statics, in addition, so let me ask you guys questions. Okay, Jason with an E. Jason, what were the 3 ways of representing a vector that we learned in the component videos? Remember? Three ways.
Yeah, I do. You could either represent it in vector form, magnitude and unit vector, or magnitude and direction.
Great. Vector form, magnitude and unit vector, and magnitude and direction angles. Right? This is the 3 ways to represent a vector. When we're doing resultants, the angles, the direction angles are what are used. I mean, I could ask you, whenever I ask you to solve for a resultant, I'm going to tell you how I want it represented. Okay? I'll be very clear about that. Okay? And if I'm not clear, then you represent it whatever way you want, and I can't take off because I didn't tell you what I wanted. Right? But for resultants, typically you want for resultants, it's common practice in statics to give the vector form and magnitude and direction angles. Does everybody see what my abbreviation is here? DIR, direction angles. So that means we have to solve for theta x, theta y, and theta z. So Jason with an O. How would I find, there's a couple of ways. How do I find what theta x is?
Is it me?
Yeah, you, Jason.
Okay.
Jason Lee.
You can inverse cosine of.
Great.
What is it? The 4 decimal number, the unit vector.
Okay. So typically, yeah, when I'm finding components, I could find the direction angles because I have the unit vectors, right? Definitely, that's one way of doing it. In this case, though, for the resultant, I don't have any unit vectors, right?
Oh,
I just added
right.
the x, y's, and z's, and I have the resultant force. So what way would I have to do it here?
Can you try inverse the resultant?
Yes.
So negative 102.1.
Excellent. 102.1 over?
The total length, the distance of the vector. Well,
you mean the resultant force, right?
Oh, yes.
Right? And the reason why is if you're choosing in the numerator to put a force, in the denominator you have to use a force too, right? When we did the components, you could put the x component of the unit vector, right, over 1, right? And if you had distances, you could put the x distance over the total distance. But in this case, the only thing we have for the resultant is the forces.
Yeah,
Okay?
and also what you have in the the argument, that is the kind of like the unit vector in the X.
Yes, that's correct. That this right here is the unit vector in the X. Jason Lee, maybe that's what you meant. Because if you're dividing the force, X component of the force over the total force, that is indeed really the unit vector in the X. So maybe that's what you meant. Okay? Now, I want to say a couple of things. One, you'll notice a lot of times I use E for unit vector. Every textbook I've taught statics out of hadn't used the variable E for unit vector. I realize that this textbook uses lambda. Has anybody looked at the textbook yet? I think it uses lambda. And I think that in math, did you use lambda?
And
okay.
physics.
In any event, I'm already in the habit of using E. So I'm probably going to wind up using E. E does seem weird, but you know, the 4 textbooks I taught out of already always used E. So, and in the end, this turns out to be 107.3 degrees. Okay, a few other things. One, notice up here, when I did the resultant force, I got a little sloppy and I didn't put a negative in here. See how the X component is negative 102.1? And when I did it here, I didn't put a negative in because I know a square of a negative is going to be a positive. But be careful, because down here, when I plugged in, Jason actually looked all the way up here and said negative 102.1. But if you leave the negative out here like I did sloppily, it's quite possible you might put a 102 and forget the negative. So be careful. Okay, so the next ones, I'm just going to write the resultant in the Y over 343.9, and the inverse cosine of the resultant in the Z over 343.9. And theta Z turns out to be 72.8, and theta Y turns out to be 24.8. And again, because I like to box my answers in, and I don't like to box all the work in, I wind up just putting theta X, theta Y, theta Z. I just write it again. So now my boxed in answers show my vector form boxed in and the magnitude and the direction angles. Is there Jordan? I didn't see Jordan. I don't know. Is Jordan here?
He's not here.
It's actually a she.
Or she's not here.
Yeah. Cody, are you ready to do this? Can you think of a check? What check can we do here? Are you still doing the component homework?
For a check, could we do, let's see.
What we just calculated were the thetas, the direction angles. How can I check those?
Do we have
guys?
a picture? Would we be able to do the visual check?
We could do a visual check, certainly,
Oh,
but let's do a mathematical one first.
would we be looking for like a magnitude check type of thing?
No, it has to do with the direction angle. Cody, let me go to another person and then I'll come back and do the visual check for you. Laura?
Okay.
Laura, how could I check these direction angles? Do you remember from the homework? You guys might remember from math, but I'm taking it in 3D. Cosine squared of theta X plus cosine squared of theta Y plus cosine squared of theta Z equals 1. You remember that from math?
Yep.
In math, you usually only saw it in 2D. You saw cosine squared theta X plus cosine squared theta Y equals 1. Well, this also works for 3D. It's Pythagorean's theorem in a way. It's really a unit vector check. So if I take cosine of 107.3 squared plus cosine of 24.8 squared plus the cosine of 72.8 squared, it comes out to 1, and it does. So that would be my check. Okay, so what did we do in this problem, just to go backwards? We had a force. We had 2 forces. We wanted to find the resultant. We noticed that they're both 3D problems. We checked to see where the axes are so we don't screw it up. We found that F1 is given distances, F2 is given angles. We found the components. We found the components of F1 did the 3 checks, found the components of F2 did the 3 checks, found the resultant by adding, using vector form. We represent adding the X, Y, and Z's. We represented the resultant as a vector form and magnitude and direction angle, which is typically how you represent resultants. Vector form and magnitude and direction angle. Okay, I have a question for you. Would you prefer, when I post the solutions, would you prefer me post what I just wrote, which, you know, all the pages are bent now and a little bit messy, or would you like me to post the nice, neat one that I wrote ahead of time? What do you want me to post?
I would probably say the neat one.
Okay, great. Okay, so now Cody mentioned, can't we do a visual check? And yeah, we can. Sometimes it's a little hard. We have 2 forces, so maybe it's not so bad, but let's take a look. We have F1 is in the positive X and F2 is in the negative X, but they're drawn to scale, right? They're drawn to scale. But this one has a 300-pound force, and this is a 200-pound force. But the 200-pound force is only going this far, and the 300-pound force is going further. My guess is the resultant is probably a negative X. But that was kind of hard to do. And is it? Yeah, it is a negative X. That's a little hard, and it might take a little too long for you to even bother doing that. But let's look at the Y. F1 is in the positive Y. F2 is in the positive Y. Of course, the Y component must be positive. How about the Z? Z is another one hard. It's negative for F1. It's positive for F2. I don't know if it's 300 going this way, but it's angled. 200 going that way. I don't know. I can't look at it right now and say, but what is our answer? It's a positive. So it's a little harder to do a visual check when you're doing resultants. Definitely in 3D. In 2D, you totally could do it. All right. Any questions on solving for resultants? Again, we are not doing parallelogram rule. The textbook does teach it. You kind of know it already. It's kind of more of a back of the napkin kind of solution, but you can draw everything to scale really nice, and it is fun, but it takes more time. I think this is the best way to go. You just crank on them. So I'm gonna stop sharing, we'll stop doing that. I'm gonna show my face, and I'm gonna look in the chat now. Okay. Okay. Any questions on solving for resultants?
Yeah, for some of the
Isaac.
3D problems in the homework, it'll have the axes, but the point that the vectors are coming off of is not the origin. In that case, would you move the axes or just run
great.
all the calculations?
Okay, great question. Okay, if a force is like this, we know the difference between scalar and vector, right? Scalar means it's 100 pounds, but you have no idea how it's flying, right? Right? You have no idea.
Yeah.
Maybe a little bit of up at bat baseball. You don't really know which way the ball is coming, but you know that person could throw it at 92 miles an hour. Okay? When it gets to you, well, then you know the vector too. Okay? So we're talking about vectors here. So if a vector is here, it doesn't matter if the tail is here at my finger, or here, or here, or here. I could pull it all the way back. Realizing right now at the beginning part of the textbook, we're all dealing with concurrent forces, which means they're all coming off the same point. So you could draw them coming from the same point. You don't have to move the axis at all. Draw them all coming off the same point. What you will use though is if it's drawn up here from the box, they might only give you the distances up here. Just use those distances because the distances are only trying to show you what the unit vector, the direction of that is. But they're all coming off the same point. So you could draw it coming off the same point. And, you know, get comfortable, watch my 3D video. I think you have to watch it by tonight anyway. You know, draw oblique. Those of you who took 25, draw obliques or isometrics, whichever one's more comfortable for you. But get comfortable drawing in 3D. Okay. Any other questions on resultants?
I have a question.
Angel?
But it's more relating to the dot product.
Okay. Let's, do we want to go into breakout groups and want me to go to Angel to do the dot product, or do you all want to hear the question, the dot product question?
I'd like to hear the question.
Okay, Angel.
I'm not sure if it was shown in the dot product lesson, but I was a little confused on how to get the unit vector for a force. But I had to look it up. So just to confirm, to get the unit vector for the force, you'd have to divide by its magnitude, right?
Yeah, so let me just show you that because you do know it already. It's just that you didn't think of it in a different situation.
Mm-hmm.
Okay, so look at this. We already know we use the dot product. If I want to get the component of force A in the direction. Now let's not do that. Let's say we already know that when I solve for the force in the x, it's equal to F times the cosine of theta x, right? We all know that. What is this? What part? This is the magnitude, right? This is the direction. What is that really? It's the x, you're trying to get, this is really the direction. So let's do it this way. Fx is equal to the magnitude of f times the magnitude of the unit vector times the cosine of theta, the angle between. Okay, and we know this becomes 1. So Fx is equal to f times the cosine of theta x. Right? So this really is representing the unit vector here in a way. The cosine of theta x, which you could say is the direction component, is equal to Fx over f. So Fx is really equal to f times the unit vector with dot product. Oh, what just happened?
Oh, my bad. I don't know what's happening. Oh.
Did you just share your screen or something, Andrew?
Yeah, I'm trying to mess around with it, but sorry.
Oh, that's okay. Just unshare it.
There we go.
So if you're trying to find, does this make sense?
Yeah.
Because we also do this, right? The force vector, can you still see my screen?
It's a little on the screen. But...
I think a good
Hang
way.
on a sec. Andrew, hang on a second.
Uh-huh.
F is equal to the magnitude of F times the unit vector. Right? Right? So F, if I wanted to find Fx, it's equal to whatever the magnitude of F is times cosine of theta xi plus cosine of theta yi j plus cosine of theta zk, right? Times whatever the units happen to be. So isn't the component of a force is equal to the magnitude of the force times its unit vector. So if you're solving for unit vector, like you said, Angel, if I'm trying to find the unit vector, it is the component over the total force.
Okay, thank you.
Okay, and I could post, do you want me to post this sheet? I'll post it.
Sure, yeah.
Can I throw in a little comment on that?
Yeah, Andrew.
Confused me too.
Please
So
do.
if you think about the dot product, imagine dotting the whole force, so F, dotted by Fx. The force Fx only has a component in the x direction. So it's going to have a 0 for the y and z. So when you dot them together, the only thing that happens is you're dotting the x component with the original force, because the y and the z component is 0.
That's a great way of explaining it. Thanks, Andrew. So we have this force, right? And we're taking the magnitude of this force and we're multiplying it by the cosine of theta x to get the x component. And the cosine of theta x is really that direction part for this. So we could find the x component by taking the magnitude and multiplying it by that cosine theta x, which is really using the dot product. Okay.
That makes more sense now. Yeah.
So I think in this case, I just explained it differently than I did in the dot product lesson, video lesson. And Andrew just explained it differently too. So you had 3 ways. And now when you go into the breakout room, you guys could explain it to each other too. Okay. And it's really, of course, you guys should be getting each other's emails. I mean, when you're at Cabrillo physically, you see each other all the time, and here you don't. So we're going into the breakout group a little bit later. We have about 10 minutes still, a little over 10 minutes. And I want you to do introductions. But if you want, get each other's email, and then you could do your own Zoom call to work on the dot product together in the evening if you wanted. Okay? All right, so I'm going to put you in breakout groups now, breakout rooms. And let's see. So we have 33, I think, for each, so that would be 8 rooms. Okay, all right, you're gonna go there. And then, you know, if you have another question for me, come back to me, or again, remember my office hours are every day 1 to 2, so I'm available today. But after the breakout room, you guys could just head out, okay? Okay, all the rooms are starting and I mean open. I think you guys join your, yeah, look, you guys are going, you totally know how to do this. And I'm going to stop the recording.